SwayamPrabha. Digital India. Educated India.
Welcome back. So, let us continue the discussion of this flame speed in the laminar premixed flame. So, we have looked at the premixed flame diagram and then how different diagram the length scale changes. So, now this is where we looked at the flame front. This is at a time instant, and there are two more information one has to find out. One is the absolute speed, which is w dot n, another is the displacement speed. That means in the how this flame front displaces. So, this is what you get. Now, one can find out the relation between the displacement speed in the species equation. Now, our species mass transfer equation will write like this, and then this is the diffusion part and this is the reaction source term. Now, our equation for the displacement speed, one can write that 1 by delta y k prime del delta E of this. Now, this particular term depends on diffusivities. So, effect is different depending on the stretch rate and curvature. And one important thing is that the differential diffusion now become quite important in hydrogen combustion, that because hydrogen has a fast mass diffusivity or higher mass diffusivity. So, that is where that unique Lewis number assumption may not work well. So, one has to be careful what kind of fuel he is dealing with, or rather what kind of flame he is dealing with, and whether that is quite applicable to the particular situation or not. So, now equation of the species mass fraction. So, that will now become, this is the left hand side or the total derivative of that, and right hand side one can express like rho SD. SD is our displacement speed, this is the displacement speed and the magnitude of the species mass fraction variance. So, now we can see how turbulent burning velocity actually in flamelet regime. So, we take that simple example of that, where we get an wrinkle flamelet like this. So, this is an, so this area one can call it AM, this is AL, and this would be ST. This is unburned site, this is burned site, and particularly this portion if one has to look at, so one can think of there is a different smaller layer like this, where this would be the SL and there would be AD of that scale. So, low intensity large scale. Now, turbulent flame speed is important. So, which we have already seen, there are different correlations exist. So, which actually now we can, from this volume we can equal the consumption rate of the unburned mixture to that. So, through which we can get an, in the flamelet regime, this is the expression which works, which we have already seen, and this is the, if you plot that U prime by SL to ST by SL, this is the flamelet theory gives, but realistically it goes like that. So, there is a deviation from that thing. Similarly, if we go to thin reaction zone regime, this is our theory says that it would be RE L naught to the power half, and this is the theory goes, but there is a deviation. So, though already we have seen there are different kind of expression which are available, but when you actually apply to the system they can vary. There is another wrinkle flamelet where you can, this is your SL and this is the ST. So, one can find out how the, or rather capturing the instantaneous flame front. So, this is another very attractive technique for premixed flame front, that we capture the instantaneous flame front by an isosurface, or rather solving an equation we will see how that is done, that capture that instantaneous flame front to get that thing. So instantaneous flame front that will propagate, and this is called the G is the isosurface, which is essentially a distance function. We will see the details when you talk about the G equation, and this is how the instantaneous flame front will propagate. And if you look at the mean flame front, so then will be mean G bar V dot del G, and this would be at the turbulent. So this is our mean flame front, this is our instantaneous flame front. So these two equations are slightly different, because when you look at the instantaneous flame front, that right hand side you have SL, the mean one propagates with a turbulent flame speed. So when you take into consideration all of this into the equation system and solution for the computational approaches, so we have to actually solve this in a quick turnaround time with chemical reactions, so one can look for simplifications. And what kind of simplifications which are possible? You can have reduced chemistry, that means you use either algebraic or tabulated reactions, so less independent variable, or you can assume the flamelet kind of assumption, local universal structure, so that is also less independent variable, or one may use statistical approach and then include the other fluctuations, or combination of something like this. So now when you again go back to the governing equations, whether it is Rands based, and when you look at this equation, these are again density weighted, your continuity equation, and then momentum equation, scalar transport equation. So there would be terms like Reynolds stress or subgrid stress. Reynolds stress, which is, so this Rands, the color corresponds to the framework, Rands framework or LES framework, this would be subgrid state. When it is Rands framework, mean source term, or it is a, in LES it is a filtered source term. When you go to turbulent scalar flux, in Rands it is a subgrid scalar flux. So the equation system, when you do Rands or LES filtering, they apparently look similar, but the terms which you get, the closure of those terms would be different, because like this in momentum, this is the Reynolds stress term which is using Boussinesq hypothesis, one can close it, or using different kind of turbulence model, but here it is a subgrid state, so it requires a different kind of closure. Similarly for source term here and subgrid scalar flux also. Now if you use the displacement speed into this governing equation, so these two set of equation won't change, but when you come to the scalar transport equation, so this is in a Rands framework, this would be mean term which is based on diffusion plus source term, or in LES it is a filtered, so that would be again diffusion plus source term, and the last term which will remain is turbulent scalar flux, which one has to basically close it, whether it is in Rands framework or LES framework. Now one can classify these models. So the classifications, already we have seen the modes of application to any mode, which is laminar, red, this is we already seen it. Models which are applicable, mixture fraction, fast chemistry based model, or non-premixed combustion, and these things. So that is what we talk about. These are the things which is applicable to any mode of combustion. These are very specific to the premixed combustion, and these are specific to the non-premixed combustion. So now we will talk about start with the BML model, which is known as Bray-Moss-Levy model, which is one of the popular model, which is initial days, which was proposed by the scientist. And so the concept which is used here is the flamelet concept. So, that is the concept behind this kind of model in the BML model. So, here we solve for a progress variable which is known as C. So, either C is defined like in terms of temperature T minus T unburned by T burned minus T unburned, or C can be defined in terms of product mass fraction which is product burned, so that it scales between 0 to 1. Now, the Fabre average transport equation, when you neglect the molecular transport, what we get, rho del C bar by del T plus rho bar ui del C by del xi minus del del xi rho bar plus omega c. So, these two terms on the right hand side, as we can see, they are not closed term. So, one need closure for that. Now, this is the turbulent transport or turbulent flux, and this is the chemical source term. So, you get this set of equations. Now, you defined a flame front like this, let us say, then you say that this is an AD size of LT, then this would be SL, and this side it is unburnt. So, C0, this is unburnt, and this side C1 which is burnt side. So, the assumption which remain there is very fast chemistry. That means the flame size, this is the LF, the flame size LF is less than LT and less than eta also. Now, another thing is that fuel conversion only in the area of the thin flame front. So, that could be in the flow field, burned mixture or unburned mixture, or intermediate states are very unlikely. So, that is another assumption which is there. You can define a flame front. So, in this thin flame front only the fuel conversion actually takes place. Now, what we say that progress variable would be 0 and 1. This is a case which is unburned, this is a case which is burned. This is solely expected to behave between 0 and 1. So, the probability density function Fc would be alpha delta C plus beta delta 1 minus C. So, if we put that thing, this is 0, this is 1, this is beta, and this is how you get alpha Fc 1, and this is C. So, this alpha and beta, these are the probabilities to encounters or to encounter burnt or unburned mixture in the flow field. So, there is no intermediate states, which means alpha plus beta would be 1, and then delta function which is defined as delta c minus c naught, which is could be infinity for c equals to c naught or 0 for constant, which gives that minus infinity to plus infinity gc delta c minus c naught dc is gc naught. So, this is how you define the, but one thing here, this probability distribution function, the definition here is that these functions are a priori assumed or presumed. That is why this flamelet kind of approach is also known as presumed PDA approach. Okay. But what we discussed, which is in hybrid combination like Lagrangian and Orion, that is a transported PDF approach where you have a transport equation for the probability distribution function. Here we solve for a different transport equation, but assuming the distribution with an a priori shape of that PDF, and that is why it is known as presumed PDF method. So, now if your instantaneous flame front go like this, then I can draw some line here where you can have this one position like this. This is my mean flame front. This is how my SL is going to behave. This is instantaneous flame front, and this side is unburnt obviously, and this side would be burnt. So, there could be one state here and there could be one state here. Now, this state, if you look at the C, this would go between 1 and 0. So, this is 1, this is how it behaves. So, that means this would be completely 1. Now, if I look at this stage here where it goes between 1 and 0. So, this is what it is and this is 1. Here along the mean flame front position, you can define that this is beta 1 C 0 alpha and somewhere 1, that is our FC, and at this, so you can have this is 0, C goes to 1, so you goes like that, it goes like that, that is 1. So, you can see that when you look at the instantaneous flame front at different situation, this is completely at the unburnt stage how this function is behaving, the probability distribution function. This is somewhere within the zone, reaction zone, this is at the mean flame front, this is at the burnt state completely. Now, we can for Fabry filtering, for Fabry averaging, one can write this is 1 by rho bar, which would be C mean to C max, U mean to U max, rho UC, F UC, DUU TC. Now, therefore, the unclosed term we can correlate like using this is the unclosed term which we can correlate this U prime by C prime using either joint PDF for U and C, which is FUC, UC equals to FC, CUC, which is the Bayes theorem, or introducing the BML approach for FC leads to that FUC equals to alpha delta C, if condition at C, UC equals to 0. So, this is an conditional PDF, or we is beta plus delta into 1 minus C FUC, where UC equals to 1, and this is our delta function. So, this is what you can close or write using BML. So, now our this quantity you can write 1 by rho bar C min to C max, U min to U max, rho Q, FUC UC, DU DC, which will allow to close this rho U bar C bar by rho bar, which is rho U minus U, C minus C divided by rho bar 1 by rho bar 0 to 1 minus infinity to rho U minus U bar C minus C bar FUC of UC DU DC, which will get you finally that C 1 minus C min U band minus this. So, this is an closure for that term. Using this BML approach, you get this simplified expression which can be used. Now, another thing is that one can use the counter gradient diffusion. So, let us say if we have a flame front like that, which is UU, UB, where rho U, UU equals to rho B, UB, this is C and this is my flame front. Now, since rho U equals to constant through flame front, rho U constant through flame front, if U increases, so rho decreases. That means my UB minus UU would be positive. Now, because C greater than equals to 0, so this term I can write C into 1 minus UB minus UU, which is greater than equals to 0. Now, this is in flame front. Now, within the flame zone, if you look at it, del C by del X, which is greater than 0. Now, if I use our gradient transport assumption, I can write U double prime would be minus dt del C by del xi, which is less than 0. So, this if you see, they are kind of conflicting each other. So, there is a conflict with the counter gradient diffusion in BML model. So, that is another thing to be noted here. Now chemical source term we can, using our Fc, leads to that Wc is 0. Now that is why we close it by flame surface density model, where Wc is written as rho u SL0 L0 summation. So this is one term, this is another term. This is our local mass conservation, this is flame surface area, per volume. L0 is our strain factor, which actually, so the strain factor, so there is always a local increase in burning velocity by strain. Now the flame surface density sigma, there is an algebraic model, I mean there could be, so this is a local mass conservation. So if you, let us say, have a frame font like this, I mean this is our mean, let us say this is our flame crossing length, which let us say Ly. Then the flame surface density, we need a closure, because this term in the source term is the local mass conservation, so which is available, and this is another term which is required. So one option is that one can use algebraic model, which is closing this term as C bar 1 minus C bar by Ly. So this is a simple expression one can use for this, or one can use the transport equation. So that is another option one can use to close up this model. So the transport equation would be in terms of xi, one can write del xi by del t plus del ui xi by del xi equals to del xi dt del xi by del xi C1 epsilon by k xi minus C2 SL xi square by 1 minus C bar. So this is our local change, this is convective change of the flame surface, this is a transport equation, this is turbulent transport, this is production due to stretching of the flame, and this is flame annihilation. So when you look at this transport equation, this is transport equation of xi, flame surface density. So the left hand side looks like any other transport equation, then right hand side you have a diffusivity, production term due to flame stretch, and the, so the other terms and the detailed analysis will continue in the next lecture. So we will stop here today.